All right, today we're doing something really cool. We're diving deep into an ancient Sanskrit text to uncover some incredibly sophisticated mathematics hiding in plain sight. And as you're about to see, the logic behind some of our most fundamental modern formulas, well, it's been around for a very long time.
So let's kick things off with a bit of a puzzle, and it seems to have nothing to do with math. We're talking poetry. Specifically, a 4-verse stanza where each verse has 8 syllables. Now, each of those syllables can be either long or short. So the question is, how many different combinations are even possible?
Get this, the answer, which they calculated way back then, is over 4 billion. No, that is not a typo. They figured out that with just 2 options, long or short, spread across 32 syllables, you get billions of unique poems. So how in the world did they figure that out without calculators, without even the symbols we use for math today?
Yeah, that wasn't just a wild guess. It was the result of using some pretty advanced math to analyze art. These ancient scholars knew that to find every single possible variation, they needed a seriously powerful tool, something that could handle that kind of rapid, explosive growth.
Okay, so to even begin to understand how they got to a number like 4.2 billion, we have to start with the core concept they had totally mastered. The text itself calls it the doubling secret, and it's the key to tackling this kind of seemingly infinite growth. So this doubling secret, well, today we call it a geometrical progression. It's what happens when things don't just add up one by one, they multiply. This is the engine behind that mind-boggling number of poems, and the text explains it with a really brilliant, simple story. Basically, all it means is you start with a number, and then you just keep multiplying it by the same number over and over again. So 2 becomes 4, 4 becomes 8, 8 becomes 16, and on and on. That number you keep multiplying by, that's the common ratio. And as we're about to see, it is incredibly powerful. And check this out. This is how they actually wrote down the rule. There are no x's or y's, no variables. It's more like a recipe written out in words. It's a set of verbal instructions that, if you follow them, gives you the sum of a geometric series. And to make this whole idea really stick, the text tells this great story about a gift to a mendicant. It starts small, just 2 little cowrie shells. But here's the catch. The gift doubles every single day. And at first, it doesn't seem like a big deal. But look at the numbers. By day 15, it's over 32,000 shells. By the end of the month, it just explodes.
So, what's the grand total after just 30 days? Over 2 billion shells. This story wasn't just some fairy tale. It was a practical demonstration. It proves they had a deep understanding of exponential growth long before you ever heard the famous story about the chessboard and the grains of rice.
Okay, but not everything grows that wildly, right? Sometimes things grow in a much more predictable, steady way. So the text also dives into that. Let's call it the second tool in their mathematical toolbox. This is kind of the opposite of that crazy doubling secret. With an arithmetical progression, you're not multiplying. You're just adding the same amount each time. So 2 becomes 4, which becomes 6, then 8. It's this steady, constant, predictable increase. And you guessed it, they've got another story to explain this one. It's about a king on an expedition. On the first day, he marches a certain distance. Every day after that, he increases his pace by the exact same amount. So the big question is, how do you figure out the total distance he traveled over those 7 days? And this is where it gets really brilliant. Look at their rule on the left. Take the last day's distance, add it to the first, cut that in half, and then multiply by the number of days. Now, look at the modern formula we use today on the right. It's exactly the same logic. They just wrote it out in a sentence instead of with symbols. But of course, they didn't just stop there. They went even further, tackling way more complex problems, like how to add up a series of squared numbers, or even cube numbers. And this is where you can really see how advanced their thinking was.
I mean, just listen to this. This is their rule for finding the sum of squares. 1 squared plus 2 squared plus 3 squared, and so on. Once again, it's not an equation, it's a set of instructions, a multi-step process that gets you the right answer every single time.
And here's that translation again, side by side. Their detailed, wordy instruction on the left maps perfectly onto this neat, compact formula we use today. The logic was already there, all of it. They just had a different way of writing it down. And then they find something just beautiful. For the sum of cubes, they figured out this incredible shortcut. They state that the sum of the first so many cubes is simply the square of the sum of the first so many numbers. I mean, that is a seriously deep mathematical insight. one that we still teach in math classes today.
And this is the crucial part. This wasn't just them playing around with numbers for fun. They used these rules as practical tools. They could work backward to find a missing piece of information. They were basically doing algebra just without the name and without the symbols.
So let's try one of their puzzles. Imagine you know how much the king increases his march each day. That's 3. You know he marches for 7 days. And you know the total distance was 105. The question is, could you work backward to figure out how far he marched on that very first day?
Yep, absolutely. The text gives you a precise step-by-step set of instructions to reverse the whole process. It's their version of rearranging an equation to solve for x. And by following their method, you find out the starting amount had to be exactly 6.
So when you put all of this together, the poetry, the progressions, the problem solving, it all points to this one really powerful idea about the timelessness of mathematical logic.
And this might be the most mind-blowing part of all. Here's their rule for finding the total time of the march when you know the start, the increase, and the total sum. It's this long descriptive sentence involving multiplication, square roots, subtraction. So what is it? It's the quadratic formula. They had figured out the logic behind the quadratic formula and were using it to solve for a variable.
And that right there is the big takeaway. When you strip away the language, the logic, the actual thinking is identical. They were performing the same high-level algebraic operations we do. They just expressed them in the most advanced written language they had at the time, descriptive sentences.
Which just makes you